Hello, welcome to the second part of the Cellular Automata series in TouchDesigner. In this video we're going to learn how to make a complete one-dimensional version of a cellular automata using a pixel shader. Before we proceed doing that, let's revise a little bit the principles. In our previous video we saw that we had a situation where a current cell was checking the left and the right neighbors to determine whether it's going to be alive or dead in the next time step. So if you do this arrangement and come up with the possible states for this, you will end up with something like this table. We also saw that this table resulted on a number of rules, which were in total 16 rules. However, in this new complete version, what we're going to be looking at is not only on the left and the right neighbors of the current cell, but also to the cell itself. So that increases quite dramatically the amount of possible rules and states. So let's see. For example, the first state will be something like this, when all the cells are dead. The second state could be something like that, where the rightmost neighbor is alive. The next one, something like this perhaps, and so on. If you come up with all the possible combinations for this arrangement, including the current cell, then you will end up with something like this table. And you will realize that you have 8 possible states for this amount of cells. The question now is, how many possible rules do we have with these states? I encourage you to pause the video, think about it, and write perhaps the first 10 rules, so you gain a deep understanding of how this works. Okay, once you have done this exercise, it is not worth to go over all the rules because they are quite numerous. So in total there's 256. We're not gonna write it by hand, but we're simply gonna generate them in a table, like I did here, using this script. So how this works is that you have all the numbers from 0 to 255, and I'm just converting them, like I did in the previous video, to their binary representation in order to have all the possible rule combinations. So if you run this, now I am filling this table, and we have all the rules in this manner. I'm doing it in a table because I want to pass this into a texture so that the texture can go inside the shader that we wrote previously. So let's go and start doing the patch for that. So let's copy this table. Let's go into our previous patch, to our previous project, and let's create a new base. I'm gonna call this base rules, and inside rules I am going to put my table. So now I need to convert this into a texture. So let's use that to chop. The first column is values as well, and then let's convert this into a top with a chop to top. Perfect. Now the resulting texture is a 8 by 256, which is exactly what I need because we have 8 possible states and 256 rules. So now we are going to put this into nearest pixel because we don't need the interpolations, and we also don't need all the RGBA channels. We only need the R channel. So this is going to be an 8-bit mono, and we need to output this so that we can use it later into our shader. Great, so that's our rule set. One extra handy thing is perhaps to have a mechanism to check the current rule. So let's do that by doing a crop here, and in the crop we're going to select the pixels mode for the bottom and top, and here we're going to select the parent rule that we created in the previous video. As you can see, this is also interpolating, so let's put it in nearest pixel, and for the crop both of these axes on the rule. So now we can visualize the current rule. So let's see. Let's for now disable the viewer here, put it on rule number 0, and if we inspect rule number 0, we see that all the values in rule number 0 are 0, which correspond to the very first rule here. Perfect. Now we need to start writing our code. So let's proceed doing that. What we need to do first is to connect these rules to our shader. We're going to use the second input. Let's do that. And now we're ready to write some code. Let's check what we did last time. So clearly we need to delete this part because now our rules are being passed via texture, so we don't need this array anymore. We can just delete it. And in the last video we defined one of the input textures as data. Let's do here the same but for our rules, and that will be on input 1, which is the second input of the shader. Great. Now let's see how we are sampling our neighbors. The cell of course remains the same, nothing changes there, but now we need to alter the way we sample neighbors, so we need to include the center cell. So let's do that using the same logic we did before. Yeah, we cannot use C because C is here, so let's do CC. And this will be vec2, 0, and -1. Because remember, -1, since we are stacking all our cells, all our rows per generation vertically. So 1, 2, 3, 4, 5, 6, etc. And we're looking to the previous one to find the current state. That's why it's -1. Alright, then we need int state right, and this would be the same as this basically, but we replace it by center cell. And our neighbors now should be a vec3 because we have 3 cells, so state left, state center, and state right. I forgot to rename this one. So let's rename this one to state center. Okay, oops. So now we have, I think, correct sampling of the neighbors, left, center, and right. Now, about the rules. Before we created that array, and it had a size of 4. Our new rule set, let's check at one of the rules in this graph we did before. This is 8 by 1. So our rule array should be of size 8. We don't need to sample it like this anymore. So let's just delete that. And now we need to define what are the values of this rule array. So we need 8, so we need to define 8 of those values. And we can do it like this. Let's just call this rule for simplicity. And let's say rule 0 is equal to the value, the first value pixel for that rule in the texture. And we're sampling from this texture. So we need to get texelFetch, and we need the input, which is the rules, and we need an ivec2. So since we are sampling from this and we want the first pixel of whatever rule we're in, let's say we're in rule 0, the first pixel will be 0. So that's 0. And then on the y-axis we need to sample the current rule. So we're 0, 1, 2, so the current rule. And this can be current rule. And we can do that here. Int current rule. Great. Now, we need to, for texelFetch, supply a level of detail argument, but in this case we don't need that. And we only need the red channel, because remember that this is a 8-bit fixed mono, so just one channel, the R channel. And let's cast this to an int, so GLSL doesn't complain, because this is a int array. Okay, and now we have the first pixel, this one. So now we need all the other ones, and we just simply copy this and paste it 7 times. 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7. So that will be this whole series of pixels. And of course our offset here should change as well. 5, 6, 7. Okay. So I think that samples the rules correctly. Now we have all of them here, and we're missing now one extra thing, which is we need to check the states like we did before. So how do we do that? We need to come up with some order to do this, and I'm gonna use the order supplied by Wolfram, and we can check that. We can check that here. If we go to Wolfram rules, so let's say this one is coming. Sorry. Yep. So if we use this one, we can see how he has formalized the rule sets. So I'm going to use this order to define this, this checking of the states. And we can see that he has done here that the black cells represent 1, so unalive, and the white cells represent a 0. So we see that 3 alive cells result in a 0, and this will be the first case. So let's see. We're going to do here neighbors vec3, and if they are equal to 1, 1, 1, so that is 1, 1, 1, then we have a 0. And is for the rule 30, but we shouldn't look at this one down. We should be looking just at the positions here. So 0, 1, 2, 3, 4, 5, 6, 7. So for the rule array, which we call rule, then we grab element 0. Then if it is 1, 1, 0, so vec3, 1, 1, 0, then our rule will be 1. And if it is 1, 0, 1, 1, 0, 1, then it's going to be 2. If it is 1, 0, 0, 0, 0, then 3. And we need some more, so let's just copy this. Oops. 3, 4, 5, 6, and 7. Okay, so 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0. Now we need to do this one. So 0, 1, 1, 0, 1, 1, then 0, 1, 0, 0, 0, then 0, 0, 1, and finally all of them 0, 0. Perfect. So now we have compared the states according to some rule set or some order, specific order. And like I said, I have used the formalized version from Wolfram. Okay. Now let's come back to this, save this thing, and let's check for the errors here. 41. Yeah, this should be all vec3. Perfect. And in 73 we have something else, and it's complaining that it's missing the current rule that we pass here. So let's supply that here, and of course this can be the uniform we already had, urule, and we are error free now. This should be basically it. So we have sampled the neighbors left, center, and right. We have grabbed the rules from our texture, and we compare the states according to some order, and we use the Wolfram order, and that's it. Let's now see if we get some patterns. Oops. So if we do, for example, rule 1, ba-bam, we have something interesting. Rule 2, rule 3, rule 4, etc. Let's see rule 30, which looked kind of interesting in the site, in the website. Aha. But if you notice something, when we look at this, we don't need the code. Well, let's just do this. If we look at the website, they usually count the rules from top to bottom. We're doing it from bottom to top. So let's just copy that for the sake of keeping it the same for now. So we're gonna use a flip just to look at it. Let's put here a null, and we're gonna feedback from the null. and let's flip this on the y-axis. And here let's just do nearest. Great, so now it's from top to bottom. And another thing you might notice, yeah, the pattern looks correct indeed. Yeah, and another thing you might notice is that when it reaches the end, this happens. And this is because on this cell there's nothing further on the left, so you cannot compare for the same rule sets that he could before. So that's what's going on here, but we don't mind about that. Maybe something we can add is the size, because this is 64 by 64. So let's create here parent.dimensions x and dimensions y. So we can change this dynamically. Let's go up and here customize the component xy. Let's call this dimensions. Nice. And now here let's say 64 by 64 like we had before. And let's try what happens, for example, if we do an odd number, 65 but 65. Everything disappears. And this is because we are doing something of a shortcut from the last video to compute the center pixel of the texture on the x-axis. So let's remedy that. We had this here, res divided by 2 for the position x. This works because of swizzling. And swizzling means that it's going to take one of the elements if you compare it to another one that has a size of 2. So res is a vec2, has 2 elements, and cpos x has only 1 element. And this works because GLSL is smart enough to give us the element we want. However, it's better to be explicit, so let's just take resolution x, because that's what we want to check. And we need to cast this to be an int, because x might give us a floating value, and this is why we don't see anything. But if we do an int, then we get this this result. Okay, perfect. So now we can do odd dimensions as well. 85 or 87 or whatever you want. Just play along. I'm gonna do as 120 by 120. Nice. Another thing we might want to do is, wouldn't it be nice to have this being generated for us? So what I mean is that you press here reset and it generates, and we can see progressively the rule that we're in, so, or the generation we're in, sorry. So let's do something like this. Why don't we add here a momentary button called reset, and we want to supply here an iteration. Let's here say iteration, or amount of iterations, better yet. And let's say we want to see the first 10 iterations. So the first 10, or maybe we should call this generations. So let's just say iterations, the first 10. And let's go inside and change a little bit our code. Here we want to see only some generation. So we say u generation. So let's say we want to see the first generation only. And for that to work, we need to alter this part here. So I guess we should do here if the c.pos.y is smaller or equal to u generation. Only then we check our neighbors and we do our calculations. And let's pass here a uniform int u generation. Okay, so now if we pass in the vector page, we have only 1 generation, 2 generations, 3 generations, and so on. So this allows us to dynamically create per generation. And I said I wanted to do this automatically. So we could do this in various ways, but let's do it in a rather simple one using a pulse here. We're gonna do pulse. We're gonna here, let's put here a new parameter called speed, or yeah, just called speed. And this speed is gonna sample at 30 frames per second. That will be the frequency here. And here we can do a counter. Great. And then let's rename this to be our generation. Okay, well, actually we'll just name it here, generation. And this is going to be going into the vector for our generation here. Nice. And now this exceeds, of course, so we need to clamp it. Let's do that. Limit, clamp min and max. And the maximum should be what we created here, the iterations, which we should just call generations actually. Let's just call generations. Nice. And now we grab this from here. And finally we sample the reset to our button here, or to our reset here, parent reset. And basically we are done with this, I think. So if we say reset and we say okay, 100 generations. And sorry, not the reset, shouldn't be here, should be on count. So we go back to 0. There we go. Now you can see how it generates up to some point. And if we reduce the speed, then perhaps the logic of this, let's put it on 6 or something, then you can see how the rules, they apply. Great. So with this, we finish this second video, and we have created a complete version of an automata. Check out other rules, which are quite interesting, and see what you come up with. So for example 90, which is I like quite a lot. Okay, great. So see you in the next video where we will cover the game of life. So that will be a 2D cellular automata system. See you then.